Hello and welcome to the LabVIEW 3-day industry bootcamp curriculum. My name is Dan. I'll be walking you through the materials today. So with your instructor packet, you should have received a number of files labeled Day 1, Day 2, and Day 3, and also a supplementary PowerPoint that I will also be going over. So the intent of this course is for industry professionals to get a leg up on exactly how they want to implement a more dynamic program in their laboratories or their manufacturing lines, is something to that effect. So apart from how we usually have our Core 1 and Core 2 and Core 3 classes, where it's just material in a booklet and exercises to accompany those that are pretty cut and dry, follow these steps and accomplish this program, we have exercises that are kind of like that, but this curriculum is meant to be more of a guideline than it is a set-in-stone material and exercises sort of curriculum how we've done in the past. So for Day 1, we have action engines, basic state machine, architecture, familiarizing them with what all the bells and whistles look like in the LabVIEW IDE, and also reading INI files, configuration files, which LabVIEW has its own palette for, and I prefer to use for this kind of application over parsing a generic text file. For Day 2, we have error handling, sequence builder, and integration that we kind of go into how to more efficiently and gracefully handle errors in a high-level application that isn't always halting execution, as is per default. When an error occurs in a LabVIEW program, we get that nasty pop-up that stops all of our execution. There's ways to log the error and not interrupt the flow of the program, and so that's a little bit of what we do in that exercise. Integration, we integrate the entire Day 1's worth of exercises, and then in the sequence builder, we use this fully integrated state machine and make a sequence generation sub-VI that we can plug into pretty much any application of a higher level giant VI of their choosing. So for Day 3, this is more of where it comes to the open end. I've attached for this curriculum in particular a traffic light CLD that I'm sure many of you who've studied for the CLD are familiar with. It's one of the easier CLDs, and it more aptly applies to this sequence generation architecture that we've laid out in the curriculum in the previous day's exercises leading up to this. But again, this is not meant to be a cut and dry series of exercises. This is more for guiding your students. You'll kind of have to feel out where their skill level is before jumping into this curriculum. If you can, study these on your own and kind of get more up to speed on how to more effectively integrate these methods into the programming than it is to just strictly follow these exercises. It'll be better for you and your students to more dynamically assess what exactly it is where they're lacking as far as putting together a dynamic state machine. So as far as supplemental materials go, if you get a class that's really greenhorns straight out of college or someone who's never been exposed to LabVIEW, these slides serve as kind of an introduction into what we are talking about in the very first day when we talk about action engines and building a monolithic state machine architecture kind of skeleton that we can use for pretty much any LabVIEW program that I would highly suggest to use in any other LabVIEW program. So action engines by definition are sort of just separate process threads that run in parallel to a main program. They can be simple, such as a counter, or they can have several different functions based on inputs and outputs and a calling program. It's basically like a proto class. If you're familiar with object-oriented programming, it allows us to do a lot of the functionality of what a programming class would allow us to do as far as separating methods and having data encapsulation without having to know very much about how to make classes, especially in LabVIEW. So this will help them hit the ground running with kind of a class level architecture without really having to know all of the ins and outs of what a class is. And like I said, retains its own data variable. For encapsulation, we go into how we exactly do that in the exercise, and it's accessible across multiple VIs and ability to pass data back and forth. So again, this is not meant to be a sort of textbook like how we had our exercise manual and the accompanying materials manual for our Core 1 and 2 classes. This is just meant to be a very high-level overview to guide a more dynamic class structure. So for state machines, this is something that I would highly recommend that you do in your class, is not just to go over the state machine exercise where we're building a state machine skeleton from scratch in the LabVIEW IDE, but actually to run through a few exercises of having your students list out and elaborate and draw out what a sort of high-level pseudocode that is the state transition diagram would look like for machines that they would encounter in their everyday life, such as an ATM, which is actually a popular CLD. I would suggest that if you have some more highly educated students to go for that CLD instead of the traffic light, but the traffic light is still a good starting point. And have them do this a few times. All of the students that I've had in my CLD courses that have really taken this approach of drawing the pseudocode first before they start programming are always the ones that pass the CLD, which is still a very small percentage. The utility of drawing the pseudocode of the state transition diagram is lost on a lot of students, and it helps to have this outside, top-down perspective on how the state machine works. And then all these cogs from the curriculum kind of fit better into place. So we would have our state machine skeleton architecture on top of this, and then we would have our separate action engines being able to control variables that are manipulated in all of these different states. And in the case of such as the ATM CLD, we have our loading from a configuration file that goes along with that just as a functional specification that's somewhat arbitrary, but necessary for that application. So again, these are not, of course, you are encouraged to go through these exercises and do them as they're written, but these are not meant in any way to be static. These, if you find your students may be lacking, it would be better to go into each of these more in depth. These are not meant to be do this exercise, achieve this result, that sort of thing. And if you find your students are more gifted than these exercises and are not presenting much of a challenge for them, there's sort of take it and run with it exercises at the end of each of these documents that accompany them, to kind of expound upon and do a more homeworky type exercise to expand their understanding of the concepts. So this curriculum is intended to teach concepts and not just, here's a program, this is how we make it, and done. This is supposed to be, how do you think about how to make a program based on what you're expecting it to do, and the guidelines of how to teach your students this mindset than it is to teach them exactly how to code it in LabVIEW, which is sort of a huge departure from how National Instruments has taught these concepts in the past, but that's how I've gotten a lot more a much higher passing rate on my CLD courses. So if you have any questions, feel free to reach out to me, and good luck.